of pressure traveling through a medium. These waves of pressure can be produced by any vibrating object, like strings of a guitar, drums, or our own vocal cords. When these vibrations hit our ears, specific nerve cells are stimulated to fire electrical signals up to our brain, which then interprets it as sound.
A tuning fork on a rubber pad and bring it close to your ear. You will hear the sound produced by tuning fork on a rubber pad and bring it close to your ear. You will hear the sound produced by it. Strike it again on the rubber pad and then touch the surface of water in a beaker with its prongs. The water in the beaker is violently agitated. Can you say the reason? Water is violently agitated because of the vibration of the tuning fork. After doing the above activities, we conclude that the kind of motion that produces sound is a rapid to and fro motion or vibration. Hence, sound is produced by vibrating bodies. Sound is a form of energy. It travels in the form of waves. There are 4 ways of producing sound. They are beating, rubbing, blowing, and plucking. Let us understand how sound is produced by doing the following activities. One end of a rubber band to a fixed support, like a nail or hook on the wall. Hold the other end with your finger. Stretch the rubber band and pluck at its middle part. Is a sound produced? Yes, a sound is heard. What kind of motion can you observe in the rubber band? The rubber band has a vibratory motion.
Sound is generated by the speaker's speech. or when an object vibrates, it sets the particle of the medium around it vibrating. The particles do not travel all the way from the vibrating object to
the plastic scale firmly at the edge of a table as shown here. Strike the loose end with your finger. Does it produce a sound? Yes, it produces a sound. What kind of motion can you observe in the scale? The scale undergoes vibratory motion.
The particles are very close together. Sound energy moves as one particle hits the other particle. With the particles being so close together, sound travels quickest through a solid. If we look at particles in a liquid, they appear to be slightly further apart when compared to solid. Thus, sound energy takes a little longer to travel through a liquid. Look at the particles of gas. They are spread out, and hence, sound waves travel most slowly.
When an object vibrates, it sets the particles of the medium
around it vibrating. The particles do not travel all the way from the vibrating object to the ear. Here, a particle of the air
The particles are very close together. Sound energy moves as one particle hits the other particle. With the particles being so close together, sound travels quickest through a solid. If we look at particles in a liquid, they appear to be slightly further apart when compared to solid. Thus, sound energy takes a little longer to travel through a liquid. Look at the particles of gas. They are spread out, and hence, sound waves travel most slowly.
Move the end of the rope back and forth just one time. One lonely crest travels through the rope. That's the pulse. Then there's the continuous wave, which is what happens when you keep moving the rope back and forth. In that case, your hand is acting as an oscillator. Anything that causes an oscillation or vibration can create a continuous wave. A vibration. Vibration is the back and forth movement of an object. In a longitudinal wave, vibrations are parallel to the direction of the wave. Sound waves are longitudinal waves.
medium of sound, air is the most common medium through which sound travels. When a vibrating object moves forward, it pushes and compresses the air in front of it, creating a region of high pressure. This region is called a compression. And when the vibrating object moves backwards, it creates a region of low pressure called rarefaction. The compressions are regions of high air pressure, while the rarefactions are regions of low air pressure. Look at this image. It shows a sound wave created by a tuning fork and propagated through the air in an open tube. These are the regions of compression, and these are the regions of rarefaction.
Sound, well, that's just another change in air density, a traveling compression wave. So Schlieren visualization, along with a high-speed camera, can be used to see it as well.
come together, you're going to see something that is normally invisible. You're going to see the actual sound wave leaving his hands and traveling outward at 761 miles per hour, the speed of sound. And here it is again. How is this possible? Well, I'll start the explanation not with landing on a table, the end of a towel being snapped, a firecracker, an AK-47, and of course, a clap.
The medium around it vibrating. The particles do not travel all the way from the vibrating object to the ear. C. This compression starts to move away from the vibrating object. When the vibrating object moves backward, it creates a region of low pressure called rarefaction, R. A compression is that part of a longitudinal wave in which the particles of the medium are closer to one another than they normally are, and there is a momentary reduction in volume of the medium. Compression is a region of high pressure. A rarefaction is that part of a longitudinal wave in which the particles of the medium are farther apart than they normally, and there is a momentary increase in volume of the medium. So, rarefaction is a region of low pressure.
Experience of hearing. Since sound needs a medium through which to travel, we cannot hear sound in space.
Closely packed together that when they vibrate, they do not move about freely, but instead they stay in a fixed position.
In liquids, the particles are constantly moving, and because they are moving, they change their position. The molecule gas particles are relatively far apart from each other. This causes the particles to be able to
The experimental setup is shown here. An electric bell is suspended inside an airtight glass bell jar. The bell jar is connected to a vacuum pump as shown here. The electric circuit is switched on. The electric current flows through the circuit. We observe that the hammer of the bell is striking the gong and sound is produced. Slowly the air is withdrawn from the jar by starting the vacuum pump. What happens to the intensity of sound? The intensity of sound goes on decreasing, and finally when all the air is pumped out of the jar, no sound is heard. The hammer of the electric bell is still seen striking the gong repeatedly. This clearly proves that a material medium is required for the propagation of sound.
In a longitudinal wave, the disturbance that makes up the wave is along the direction in which the wave travels. Longitudinal waves are also referred to as compression waves.
The medium is simply the material through which the disturbance is moving, and it can be thought of as a series of interacting particles. Typically, this medium is air, though it can be water or wood. There has to be a source of the wave, a vibrating object capable of disturbing the first particle of the medium, like a guitar string or a tuning fork. The sound wave is transported from one location to another by means of particle-to-particle interaction, with each particle causing a disturbance of its nearest neighbors. Because of the longitudinal motion of the air particles, there are regions where the particles are compressed together and other regions where the air particles are spread apart. These regions.
In a transverse wave, the disturbance that makes up the wave is perpendicular to the direction in which the wave travels.
That here by looking at a lovely rubber duck sat in a bath. As a wave goes through, the duck bobs up and down, but once the wave's gone, he's back to his original position. The wave has carried energy through, but it did not carry the duck with it.
Ray is now shaking a rope up and down. He is transferring energy to the rope, and the rope transports this energy in a repeating oscillation, a wave. We see movements in two directions here. The wave starts at Ray's hand and moves forward. We call this movement propagation. The wave propagates forward. The second movement is the direction of the oscillation. Look at this red dot on the rope. It moves up and down. So the rope wave oscillates at a right angle to the wave's propagation. A wave that moves in this way is called a transverse wave.
Theory of light. Light is part of electromagnetic radiations. Radiations which are produced by oscillation of electrically or magnetically charged bodies are called electromagnetic radiations.
Two consecutive compressions or rarefactions. The number of waves passing through a point in a second is called frequency.
The peaks with crests, the bumps on the top, and troughs, the bumps on the bottom, they have an amplitude, which is the distance from the peaks to the middle of the wave. They also have a wavelength, which is the distance between crests, a full cycle of the wave, and a frequency, which is how many of those cycles pass through a given point.
Raised from its equilibrium position, it then exerts a force on adjacent particle. The adjacent particle gets displaced from its position of rest. After displacing the adjacent particle, a compression is that part of a longitudinal wave in which the particles of the medium are closer to one another than they normally are, and there is a momentary reduction in volume of the medium. Compression is a region of high pressure.
Longitudinal waves, where the oscillations happen in the same direction as the wave is moving. These are the kinds of waves that you get by compressing and stretching a spring, and they're also the kinds by which sound travels, which we'll talk about more next.
There are regions where the particles are compressed together, and other regions where the air particles are spread apart. These regions are called compressions and rarefactions respectively. There are regions where the particles are compressed together and other regions where the air particles are spread apart. These regions are called compressions and rarefactions respectively.
The distance between two consecutive compressions or rarefactions.
A complete sound wave can be considered as the repetition of the pattern of a single wave. That is, it consists of a number of compressions and rarefactions in succession. The length of a single wave is called its wavelength. In other words, wavelength is the distance between two consecutive compressions or two consecutive rarefactions. It is denoted by the Greek letter lambda.
Heinrich Hertz was the first to send out and receive radio waves. He was born in 1857 in Hamburg, Germany. His breakthrough led to the invention of the radio. He proved that radio waves are electromagnetic in nature. The frequency of radio waves was named Hertz in his honor. He died in Bonn, Germany in 1894.
And we can see that here by looking at a lovely rubber duck sat in a bath. As a wave goes through, the duck bobs up and down, but once the wave's gone, he's back to his original position. The wave has carried energy through.
The number of waves passing through a point in a second is called frequency, and it is measured in hertz.
We have a graphical representation of the whole thing. This demonstrates quite clearly how they all relate to each other. So if I play it, we have at the top, right here, we have our longitudinal wave or sound wave. And below that, we have our displacement, and below that, we have our pressure. Some things to point out and to show is that we can see in the representation of the sound wave right at the very top, we can see regions of denser particles and less dense particles as the wave oscillates. That corresponds to our compressions and rarefactions. Another two things to point out is that we have both nodes in displacement and nodes in pressure. A node, of course, being where the displacement, or not the displacement, but where the function crosses through the equilibrium position. So for our displacement node, which we have right here, this would represent a region where there is no change in displacement. So we can see, interestingly enough, by comparing the two bottom graphs, that at a node in displacement, we have an antinode in pressure. So this we can see on the top representation right here around the first red dot. You can see here that the local density does not change where, or I should say, the local displacement does not change, where the particles in that vicinity do not actually move. But we can see as the wave oscillates, we have both maximums and minimums in the pressure. Another thing to point out is our node in pressure, which we can see taking place at the last dot. We know that the node in pressure and occurs at the antinode in displacement.
Disturbance that makes up the wave is along the direction in which the wave travels. Longitudinal waves are also referred to as compression waves.
Reciprocals of each other. In other words, if you know the frequency of something, you can get the period by just taking 1 divided by the frequency. Likewise, if you know the period, you can get the frequency
what eyes they were. And what eyes they were.
The amplitude of the wave and the pitch depends on the frequency. High frequency sound waves sound high pitched and vice versa. Human beings
Amplitude, time period, frequency. Amplitude. Amplitude of the sound is nothing but the loudness or the amount of maximum displacement of the particles while the sound is produced. When the amplitude of the vibration is large, the sound produced is loud. When the amplitude is small, the sound is feeble.
Need a metal glass and a spoon. Pour some water in a metal glass. Now strike the glass with a spoon and observe the sound. First softly, then a little harder, and again very hard. You observe that the loudest sound is produced when the glass is struck the hardest. Now we will test the amplitude of the sound waves. Keep the glass near a thermocol ball which is hanging from a string. Let the ball slightly touch the glass. Now again strike the glass and observe the ball. We see that the thermocol ball gets displaced more when the glass is struck harder. This shows that the glass vibrates with more amplitude when it is struck harder. So we can conclude that difference in loudness of sound is due to difference in the amplitude of waves it produces.
hear the horn of vehicles, crying of babies, sound of crackers, loudspeakers, etc. Some unpleasant sound called noise. The loud and unpleasant sound or noise is
Finally, frequency, which is the number of complete waves to pass a point every second. And it's given the unit of hertz. So an example of this would be if 10 waves pass in 2 seconds, the frequency would be 5 hertz. Using these things, we can actually now calculate the speed of a wave using the equation speed equals frequency times wavelength, or to give it in symbol form, V equals F lambda.
In this module, you will learn about the characteristics of sound waves. A complete sound wave can be considered as the repetition of the pattern of a single wave. That is, it consists of a number of compressions and rarefactions in succession. The length of a single wave is called its wavelength. In other words, wavelength is the distance between two consecutive compressions or two consecutive rarefactions. It is denoted by the Greek letter lambda. Since a compression and a rarefaction follow each other in succession, sound propagation is a periodic phenomenon. The interval between the generation of two successive compressions or two successive rarefactions is constant and is referred to as the time period of the wave. Time period is denoted by T and is measured in seconds. Frequency of sound is the number of waves produced in unit time. It is denoted by the letter N and is measured in hertz. The relationship between frequency and time period can be expressed as N is equal to 1 divided by T, where T is the time period. Thus, if the time period of a wave is 1/10 of a second, then we get 10 waves in 1 second. The frequency of this wave is 10 Hz. Listen to this scream and the cooing of a pigeon. Why is the effect of the two sounds on our ears so different? It is related to a concept called the pitch of sound. Pitch is the interpretation of the frequency of a sound by the brain. Commonly, pitch is taken as the frequency of sound. A scream is a high-pitched sound, since the frequency of a scream is high. Similarly, the cooing of a pigeon is a low-pitched sound. The shorter the wavelength, the higher the frequency, and the higher the pitch of the sound. Simply put, short waves sound high. Long waves sound low. Let's listen to some music. Is it a single instrument or two instruments playing? It is definitely two instruments. One sounds like a violin and the other could be a sitar. We could identify the difference in the instruments because of the type of sound we heard. Sound emitted by every instrument has a unique characteristic that distinguishes it from other sounds with the same pitch or loudness. This characteristic is the quality or the timbre of the sound. If we listen to either instrument playing the same tune separately, we can make out the difference in the quality of the two sounds. Sometimes, when you switch on your computer, you can hear a long beep indicating a boot-up error. Listening carefully, you make out that this beep is a uniform sound. This beep sound has a single frequency. Thus, the sound wave shows uniformity. This is an example of a tone. A tone is a sound wave of single frequency. A man on the left seems to be listening to some good music. A proper mixture of frequencies results in a pleasant sound or note, which we term as music or musical note. Thus, a note is a sound produced due to a blend of several frequencies. If a note is not pleasant to hear, it is simply called noise. Now, listen to these sounds. Can you hear me? Can you hear me? One sound was loud and the other was very soft. What makes these sounds different? It is a characteristic called amplitude. The loudness of a sound depends on its amplitude. The amplitude of a sound wave is the maximum displacement of the vibrating particles from their mean position. It is represented by the letter A and depends on the force with which an object is vibrated. The greater the amplitude, the louder the sound heard, and the lesser the amplitude, the lower the audibility of the sound. Listen to these two sounds produced by the same drum. The second sound was louder than the first. This is because the amplitude of the sound produced the second time was higher. A loud sound can travel across a larger distance because it is associated with higher energy. Let's now look at the speed of sound. Speed is the ratio of distance to time. For a sound wave, The distance is its wavelength, lambda. And the time is the time corresponding to the wavelength, which is time period t. Therefore, the speed of a sound wave is the ratio of its wavelength to its time period. It is denoted by the alphabet V. The reciprocal of the time period of a sound wave is equal to its frequency. Therefore, the speed of a sound wave is the product of its frequency n and wavelength lambda. A tone is a sound wave of a single frequency. A note is a sound produced due to a blend of several frequencies. Amplitude A is the maximum displacement of the vibrating particles from their mean position. Speed is the ratio of distance to time. It is denoted by the letter V.
We hear a variety of sounds around us. We hear some sounds around us that are soft. Some sounds, on the other hand, are very loud. Some sounds we hear are shrill. Also, we get to hear some sounds of low pitch. Some sounds appear pleasant to us, and we look forward to hear such sounds, whereas some sounds make us feel annoyed. Before understanding what makes these sounds different from each other, let us recapitulate how a sound travels. We know that sound is a longitudinal wave, and sound waves move in a medium as a series of compressions and rarefactions. We can also represent sound waves simultaneously in a density or pressure graph. Compressions, as we know, are the regions where the particles are crowded together. These regions are represented by the upper portion of the curve. The peak represents the region of maximum compression. Thus, compressions are the regions where the density as well as the pressure is high. Rarefactions are the regions where the particles are spread apart and are represented by the valley, that is, the lower portion of the curve in the figure. Here also, the extreme bottom point represents the region of maximum rarefaction. Thus, rarefactions are the regions where the density as well as the pressure is low. A peak of the curve, representing compressions, is known as a crest, and that of the valley, representing rarefactions, is known as a trough of the wave. The distance between two corresponding crests or two corresponding troughs, or the distance between compressions or two consecutive rarefactions, is called the wavelength of the wave. The wavelength is represented by the Greek letter lambda. Its SI unit is meter. Thus, we have seen that all sounds can be represented by waves. Each sound has its own wave. Each wave has certain characteristics that make the sounds around us different from each other. These characteristics are frequency, amplitude, and quality. Let us learn about the characteristics of sound waves and their effects on the same. Let us start with frequency. Frequency tells us how frequently an event occurs. Suppose you are beating a drum. The number of times you beat the drum per unit time is called the frequency of the drum. If we beat the drum 10 times in 1 minute, we can say that its frequency is 10 beats per minute. We know that when sound waves propagate through a medium, the density of the medium oscillates between the maximum value and the minimum value. the change in the density between the maximum value to the minimum value and again to the maximum value makes a complete oscillation. The number of oscillations per unit time is called the frequency of the sound waves. Similarly, if we count the number of compressions or rarefactions that cross a particular region per unit time, we will get the frequency of the sound wave. Frequency is denoted by the symbol F and its SI unit is Hertz. 1 Hertz is defined as 1 oscillation or 1 cycle per second. Once we know the frequency, we can also get to know the time taken for one complete oscillation in the medium. That is, the time taken by 2 consecutive compressions or rarefactions to cross a fixed point. This is known as the time period T of the wave and is given as T equals 1 upon frequency F. Its unit is second, S. Frequency is interpreted by our brain as pitch. It is the pitch that makes us differentiate the frequency of 2 sounds. To understand this, let us consider these 2 sounds: blowing of a whistle and cooing of a cuckoo bird. In case of a blowing whistle, the waves are moving fast and hence the frequency is high. Thus it produces a high-pitched sound or shrill sound. Now let us come to the case of a cooing cuckoo. Here the waves are moving slow and hence the frequency is low. Thus the cooing of a cuckoo is a low-pitched sound. Thus, the faster the vibration of the source, the higher is the frequency and higher is the pitch corresponding to that sound. Let us now come to another characteristic of sound, that is, the amplitude. The maximum disturbance in a medium on either side of the mean position gives us the value of the amplitude of the wave. It is defined as the magnitude of maximum displacement of each particle from its mean position. It is represented by the letter A. Its SI unit is meter. It depends on the force with which the object is made to vibrate. If we strike a drum with lesser force, that is, if we strike a drum lightly, we hear a soft sound, as the sound produced is of low amplitude. However, if we strike the drum with more force, that is, if we strike the drum hard, we hear a loud sound, because in this case, the sound waves have large amplitude. Hence, the amplitude of the sound wave determines the loudness or softness of sound. Let us now learn about the third characteristic of sound, that is quality. For this, let's listen to some music. Is it a single instrument or are 2 instruments playing? For sure, there are 2 instruments playing. One sounds like a violin and the other one a sitar. Both the instruments were producing the sound with the same pitch and loudness. But still, we could identify the difference in the instruments because of the type of sound they are producing. The sound produced by every instrument has a unique characteristic that distinguishes it from other sounds with the same pitch and same loudness. This characteristic of sound is the quality or the timbre of the sound. The sound which is more pleasant to hear is said to be of a rich quality. The sound produced by both the violin and sitar are pleasant to listen to. Thus, these sounds are of rich quality. On the other hand, the sound produced by a tuning fork is not pleasant to hear and hence is of poor quality. Similarly, music is pleasant to hear whereas noise, as in case of sound from vehicles and machines, is unpleasant or irritating to our ears. Thus, the sound of music is of rich quality, whereas that of noise is of poor quality. This is how the characteristics of sound, that is, frequency, amplitude, and quality, make the sounds around us.
He never broke it, but he was flirting with it.
In a solid, the particles are very close together. Sound energy moves as one particle hits the other particle. With the particles being so close together, sound travels quickest through a solid. If we look at particles in a liquid, they appear to be slightly further apart when compared to solid. Thus, sound energy takes a little longer to travel through a liquid. Look at the particles of gas. They are spread out, and hence, sound waves travel most slowly through them.
During summer season, the temperature of air increases. At higher temperature, the molecules of air have more kinetic energy. Hence, they vibrate faster, leading to increase in speed of sound. Now, during winter season, the temperature of air decreases. With the decrease in temperature, the kinetic energy of the molecules also decreases. Hence, the molecules do not vibrate much. As a result, the speed of sound decreases during winter season.
Speed of sound in different media. The speed of sound depends on the material through which it's passing. It is greater in solids than in liquids or gases because the molecules in a solid are closer than in a liquid or gas. In this table, you can find the speed of sound in different media at 25 degrees Celsius.
Над дорогой смотрите. Ой, мамочка, ой, страшно.
Yeah, he got it. Oh, he got it.
Quebrou? Quebrou, cara? Eu vi tudo no chão.
Reflection of sound. Sound is a part of our everyday sensory experience. So how is sound produced, propagated and detected? A good model is the stethoscope, used to listen to the sounds of heart and lungs. But how are these sounds heard? To understand this, we need to know what reflection of sound is. When sound travels through a medium, it strikes the surface of another medium and bounces back to the original medium. This phenomenon is called the reflection of sound, which obeys the laws of reflection. The first law states that the angle of incidence is equal to the angle of reflection. We can provide this by placing two tubes at certain angles on a wooden board. If a clock is placed near the end of one of the tubes, we can hear the sound waves through the second tube by adjusting it to get the sound at its maximum. We can see that the angle of incidence is equal to the angle of reflection. The second law states that the incident wave, the reflected wave, and the normal at the point of incidence all lie in the same plane.
Loudness, pitch, and quality of sound. Musical notes is produced when a vibrating object such as drum, guitar causes disturbance to the air particles in a regular frequency. Musical notes can be distinguished from each other by their three characteristics, that is loudness, pitch, and quality. Loudness refers to how loud or soft a sound seems to a listener. The loudness of sound is determined by the intensity of the sound waves. Intensity is a measure of the amount of energy in sound waves. The intensity of a sound wave is directly proportional to the square of the amplitude. The following waveforms displayed on the CRO screen shows the effect of amplitude on the loudness of sound. The bigger its amplitude, the louder the sound is. The sound becomes softer when the amplitude is smaller. For example, a person strums a guitar harder to increase the energy and amplitude of vibration, thus producing a louder sound. How high or low a sound seems to a listener is its pitch. Pitch depends on the frequency of sound waves. The following waveforms displayed on the CRO screen shows the effect of frequency on the pitch of sound. The higher the frequency of sound, the higher its pitch. When the frequency is lower, the wavelength is longer, thus pitch is lower. To produce a note of higher pitch, the frequency of the vibrating strings can be increased by increasing the tension, shortening its length, and using a thinner string of smaller mass per unit length. Most musical instruments have a way of changing the frequency of the sound waves they produce. Different musical instruments produce sound of different quality. A note played on a musical instrument is a blend of the fundamental of the lowest frequency and overtones of higher frequencies. The quality of a note is determined by the overtones. These overtones can be identified from the waveforms on the CRO screen, produced by different instruments. Thank you for taking time to watch this.
Also suffer reflection from large obstacles. If we stand at a distance from a high wall and clap our hands, we can hear the same clapping sound after the dying out of the original sound. This is called an echo. Therefore, for an echo to be heard, the time interval between two sounds must be 0.1 seconds. As sound travels at a speed of 340 meters per second in air, the distance traveled by sound in 0.1 seconds is 34 meters. Therefore, to hear an echo, we need to stand at least 17 meters away from the wall. What happens if there are 4 enclosed walls that are less than 17 meters away? What we experience here is a reverberation that is due to multiple reflections of sound from the walls, roof and floor, which follow so closely behind the original sound that the original sound appears to be prolonged even when the source of the sound stops. We can thus say that reverberation is the multiple reflections of sound waves, whereas echo is the single reflection of sound waves. However, excessive reverberation makes the sound indistinct, which can be a setback in auditoriums. This can be reduced by using sound-absorbing materials like ceilings made of soft and textured materials and flooring made of acoustic tiles. Certain technologies make use of the multiple reflections of sound. To name a few, we have megaphones, hearing aids, soundboards, stethoscopes, and the curved ceiling of concert halls.
When you hear thunder rolling, the sound continues for some time. The rolling of thunder is due to the successive reflections of sound from a number of reflecting surfaces, such as the clouds and land. This is called multiple reflection of sound. Thus, multiple reflection of sound is the successive reflection of sound from various reflecting surfaces. The curved ceilings of cinema halls and conference halls are also designed keeping the principles of multiple reflections in mind. The curve in the ceiling ensures that the sound is reflected to all the corners of the hall, so that there is an even distribution of sound. In some cases, a soundboard is positioned behind the stage so that the sound waves produced are spread across the hall evenly. However, in cases where these halls are not designed properly, multiple reflections can lead to uneven distribution of sound. Let's see what causes this problem. Consider a big closed room where a source S, a speaker, and an observer O are in the positions as shown. The observer may hear more than one reflection of sound produced by the source. This is due to the multiple reflections produced at different locations on the walls and in the room. This can make it difficult for the observer to focus on what the speaker is saying and hear him clearly. The reflected sound is heard until its intensity is reduced to a value where it is no longer audible. Finally, the sound fades off completely. Thus, the observer hears the sound produced by the source persistently till it fades away beyond audibility. This phenomenon of persistence of sound in a closed enclosure, due to the multiple reflections of sound in an enclosure, is called reverberation. Reverberation is generally minimized in auditoriums by covering the walls, the ceiling, and the flooring using sound-absorbent material like cardboard, thick curtains, and fiber. There are various other applications of multiple reflections. Megaphones, horns, and musical instruments like trumpets are designed to magnify amplitude of the sound and reflect and propagate sound waves in a particular direction. A doctor using a stethoscope to give you a checkup is a very common sight. A stethoscope uses the principle of multi-reflections to help the doctor hear your heartbeat. Let's take a look at how it works. The chest piece of the stethoscope consists of a plastic disc called the diaphragm, which is placed on the patient's body. The sound of the heartbeat vibrates the disc. These vibrations produce pressure waves which travel to the listener's ears through the hollow tubes by a series of multiple reflections throughout the tubes. Consider a big closed room where a source S, a speaker, and an observer O are in the positions as shown. The observer may hear more than one reflection of sound produced by the source. This is due to the multiple reflections produced at different locations on the walls and in the room. This can make it difficult for the observer to focus on what the speaker is saying and hear him clearly. The reflected sound is heard until its intensity is reduced to a value where it is no longer audible. Finally, the sound fades off completely. Thus, the observer hears the sound produced by the source persistently till it fades away beyond audibility. This phenomenon of persistence of sound in a closed enclosure, due to the multiple reflections of sound in an enclosure, is called reverberation. Reverberation is generally minimized in auditoriums by covering the walls, the ceiling,
and the flooring using sound-absorbent material like cardboard, thick curtains and fiber. Hearing aids help us compensate for any shortcomings in our hearing capabilities. So, how does a hearing aid work? A hearing aid is a battery-operated device that receives sound waves through a microphone. This microphone converts sound waves into electrical signals, which are amplified by an amplifier. The amplified signals are sent to the speaker of the hearing aid. The speaker converts them into sound waves and sends them into the ear at a volume that the ear can clearly hear. The buzzing of a bee is clearly audible. In fact, sometimes we wish it wasn't so loud. However, though we can see the pendulum vibrating, it doesn't seem to be producing a sound. Look at the boy straining to hear the sound of the pendulum. We are unable to hear some of the sounds produced around us because sounds vary in their frequencies. A human ear can only hear sounds that are within a frequency of 20 Hz to 20,000 Hz. This range of frequency is called the audible range. We cannot hear sounds with a frequency lesser or greater than this audible range. However, the audible range for different species is different. Dogs, for example, have an audible range much higher than that of humans. That's why people have watchdogs. Dogs can hear many sounds that are not audible to human ear. The table shows the hearing range for 3 animals. Dogs can hear sound waves ranging from 18 kHz to 22 kHz. Rhinoceros can hear sound waves ranging from 0 Hz to 5 Hz. Bats can hear sound waves ranging from 0 Hz to 100 kHz. Sound waves that have a frequency less than 20 Hz are called infrasonic sound waves. These are also referred to as infrasound waves or infrasonics. Similarly, sound waves that have a frequency greater than 20,000 Hz are called ultrasonic sound waves. These are also referred to as ultrasounds or ultrasonics. A summary of the various ranges of sounds is shown here.
Range of hearing. The average person has a normal hearing range that falls between 20 Hz on the low side and approximately 20,000 Hz on the high side. Children under the age of 5 and some animals such as dogs can hear up to 25 kHz. The hearing range of humans gets worse with age. People lose the ability to hear sounds of high frequency as they grow older. Sounds of frequencies below 20 Hz are called infrasonic sound or infrasound. Some animals like whales and elephants produce sounds in the infrasound range. Frequencies higher than 20 kHz are called ultrasonic sound or ultrasound. Dogs can hear some ultrasound, thus a dog trainer can use an ultrasound whistle to call his dog. Ultrasound is even more important for bats because they rely on ultrasound to see the world.
Of ultrasound. Frequencies higher than 20 kHz are called ultrasonic sound or ultrasound. Ultrasounds are used extensively in industries and for medical purposes. In industries, ultrasounds are used to detect cracks and flaws in metal blocks. These cracks and holes are not visible from outside, but they reduce the strength of the metal. To detect the flaws in the metal block, ultrasounds are allowed to pass through the metal block, and the detectors are used to detect the transmitted waves. If there is a small defect or flaw the ultrasound gets reflected back. This indicates the presence of the defect in the metal block. Note that the ordinary sound of longer wavelengths cannot be used to detect flaws in metals, as it will bend around the corners of the location and enter the detector. Ultrasound is used to clean parts located in hard-to-reach places. For example, spiral tube, odd-shaped parts, electronic components, etc. The object to be cleaned is placed in a cleaning solution, and ultrasound waves are sent into the solution. Due to their high frequency, the ultrasound waves struck the cleaning solution. Because of stirring, the particles of dust and dirt get detached and drop out the object, thus get thoroughly cleaned. Ultrasound are used in echocardiography, ultrasonography, and to break small stones in kidneys. Echocardiography is the technique in which ultrasonic waves are made to reflect from various parts of the heart and form the image of heart. This helps the doctor to examine the heart. Ultrasonography is the technique of obtaining images of internal organs, like kidney, liver, gallbladder, uterus, etc., of the body, by using echoes of ultrasound pulses. Ultrasonic scanner is used to get those images. In this technique, the ultrasonic waves travel through the tissues of the body and get reflected from a region where there is a change of tissue density or a defect. These waves are then converted into electrical signals to generate image of the organ. These images are then displayed on a monitor or printed on a film. Thus, from these images, the internal organs can be examined. Ultrasonography is also used to monitor the growth of fetus and detect the congenital defect, if any. Ultrasound may be used to break small kidney stones into fine grains. These grains later get flushed out with urine.
Sonar. Sonar stands for Sound Navigation and Ranging. It is a device which uses ultrasonic waves to measure the distance, direction, and speed of underwater objects and helps mariners to investigate the nature, size, and location of the object so that potential threat to the vessel is identified and overcome. How does it work? Sonar has a transmitter and a receiver which are installed at the bottom of the ship. The ultrasonic waves transmitted by transmitter travel underwater and get reflected back from obstacles. The detector receives the signal and converts it to electric signal. A computer forms image of the obstacle and displays it on a monitor. It also calculates distance of the object using this formula. Distance is equal to speed into time upon 2. Speed is equal to speed of sound in saline water equal to 1530 meters per second. This method is called echo ranging. The sonar technique is installed in every ship to determine the depth of the sea and to locate underwater hills, valleys, submarines, icebergs, and sunken ships, etc., to avoid a disaster.
frequency. If the wavelength of sound wave is bigger than the size of prey, sound waves can be considered to directly pass them. A higher frequency results a shorter wavelength, so that the sound will reflect when it reaches the prey. If the prey is flying toward the bat, frequency of the echoes is higher than the frequency of the sound that the bat sent. And if the prey is flying away from the bat, frequency of the echoes is lower than the frequency sent. By knowing the duration from the time it shouted till its own echo is heard, bats can determine how much time is needed to reach a prey.
The human ear. Hello students, welcome to the present session. We all know which organ helps us to hear. Ear is a sensitive device which functions with hearing. Ear allows to convert audible frequencies into electric signals that travel to the brain. These signals travel to the brain through a nerve called as auditory nerve. Now let us learn about auditory mechanism of human ear. The human ear is mainly classified into three portions. 1. Outer ear. 2. Middle ear. 3. Inner ear. Outer ear. The outer portion of the ear is called as pinna. It collects sound from the surroundings and passes through auditory canal to the eardrum. Eardrum is a thin membrane present at the end of the auditory canal, also called as tympanic membrane. As we already learned, sound wave consists of compressions and rarefactions. When the compressions of the sound medium reaches the eardrum, the pressure on the outside of the membrane increases and forces eardrum inwards. In the similar way, during rarefaction, eardrum moves outward, thus eardrum vibrates. Middle ear. The middle ear consists of three bones. 1. Hammer. 2. Anvil. 3. Stirrup. The vibrations of the eardrum are amplified many times by these three ear bones. Also, the middle ear transmits amplified and pressure variated sound waves to the inner ear. Inner ear. The pressure variations of the wave are turned into electrical signals by cochlea. The electrical signals are passed through auditory nerve to brain, and brain interprets them as sound. Well students, this is all about auditory mechanism of human ear.